Okay, so right, let's just start for today. Okay, so our goal for today is not just to finish the notes because we definitely can, but to do some rather challenging tutorial questions now. Okay, because I feel that atomic structure, because it's too easy, a lot of people underestimate this chapter. And then they just think that okay, no need to study. But then come out the exam, right? The questions can be quite tough. Okay, so today we are more question oriented. Okay, so anyways, today, right, we will finish up whatever we talked about, but we were on physical properties, or more likely physical trends, right? Now, when we discuss physical trends, in the last lesson I discussed, right, there are two ways to navigate the periodic table. Okay, either down the group or across a period. Now, can you remember, right? Okay, because there's a lot of writing in this chapter, and I want to minimize the amount of memory work. When you go down the group, right, what's the first thing they need to explain? Good. Okay, basically we're going to use the term, the number of quantum shells, right? The number of quantum shells will always increase down the group, and that will allow us to explain many, many different properties. So for example, atomic radius. Okay, of course, if we get bigger and bigger, more shells, so atomic radius will increase. Last lesson, we also learned the idea of ionization energy. It is the energy needed to remove an electron, right? Okay, we need to remove an electron using energy because there's some sort of attractions that are holding it back. Okay, and we call that the electrostatic forces of attractions. Okay, but anyways, okay, because of that, right, this is quite simple and I already covered it. Today we're going to discuss direction of across a period. But this time round, right, unfortunately, we cannot use the number of quantum shells because it doesn't change. So we're going to learn something new called effective nuclear charge. Okay, I think what you can do, right, split back a few pages because a few pages back, they actually explain what effective nuclear charge is. But I'm just going to explain from scratch. Okay, so how it works is this. When we have an effective nuclear charge, okay, what's nuclear charge and all that? Just to make things a bit simple for us, right? Nuclear charge, in a very simplistic term, just means how attractive is the nucleus. Okay, nuclear charge is how attractive the nucleus is. And do you know, right, what affects how attractive the nucleus is? What affects the attractiveness? What makes a nucleus attractive in the first place? What does it have that can attract electrons? Okay, a nucleus contains protons, right? So the protons will attract the electrons. So if you have more protons, do you think it is more attractive or less attractive? Definitely more attractive. Okay, so it's the same idea over here. Okay. So clearly, right, okay, when we go across a period, the number of protons will definitely change. And to discuss what effective nuclear charge is, I think it's very good for us to use this little equation to help us with answering the questions. So as you can see over here, this is called effective nuclear charge. Z represents nuclear charge. Okay, this is effective. Effective nuclear charge is nuclear charge minus this thing called shielding effect. Once again, there are no calculations in this chapter. It's just to help us understand and compare the different factors. Okay, so just to help us with our reasoning later on, right? This is nuclear charge. And as we have already discussed, nuclear charge is affected by the number of protons. If an element has a lot more protons, then clearly the nucleus is more attractive. Make sense? Okay, but then what is shielding effect? Okay, so let's think about this. Now, it could be as simple as discussing how attractive the nucleus is. However, there's some sort of shield going on. Why? So let me just show you first. Shielding effect, right, is affected by the number of inner shell electrons. So basically, these are the factors that you should keep an eye out for whenever you want to explain any of these factors. Okay? So let me explain what shielding effect is first, using a very simple diagram. Okay, you can visualize this as a nucleus. Nucleus is positively charged, and it is trying to attract the valence electrons. So imagine this is a valence electron, and clearly there's some sort of attractions over here, right? However, there's another problem. Okay, if you realize, right, there are many, many inner shells. And do you realize that these inner shells are basically blocking the attractions between the nucleus and the valence? Now, I think about it logically. If there's only one electron, do you think there's a lot of blocking happening? No, it's very empty, right, the shell. So the attractions are still rather strong. However, if you have a bunch of electrons, I really got like 7 or even 8 electrons in that quantum shell, do you think there's a lot of blocking going on? Yes. And if there's a lot of blocking, right, you can think of it as an umbrella from like the wind, right? Okay, there's a lot of blocking going on, so the attractions here are going to be stronger or weaker. Yes, that's why, right, shielding effect has a negative sign. The higher the shielding effect, the okay. Okay, so I'm just explaining a very rough idea of what we're going to do today. Okay, so last lesson, you remember we went through a number of quantum shells, right? Okay, that was a very easy idea. Okay, but today we're looking at this thing called effective nuclear charge. Okay, just to complete whatever I was saying first. Nuclear charge depends on 2 factors. Number 1, how attractive is the nucleus, which depends on how many protons you have, right? The more protons you have, the more attractive the nucleus. Does that make sense? Okay, that's very simple. But the harder idea to digest, right, is this thing called shielding. You need to understand, right? If there's so many electrons on the inner shell, there's going to be a lot of blocking going on. So that's why the attractions are going to be weaker. So just understand this first, okay? If there's less inner shell electrons, is there a lot of blocking, a lot of shielding going on? No. So that means the attractions are going to be higher or lower? Higher. Okay, so you see, the lower the shielding effect, the higher the effective nuclear charge. That's why there's a negative sign to offset this idea. Okay? It's not about just how attractive it is, but it depends on how many electrons are in the inner shell to block the outer shell. Okay, later we look at how some examples will showcase this. Okay, but for now, you'll just need to have this idea in your head that there is an inner shell trying to block the attractions. All okay so far? So we're just going to dive straight into the trends and then we will understand how this works. So can you turn over to page 24? Yeah. So as I mentioned now, guys, it's a lot harder to explain trends across a period. So if you turn over to page 24, right? Okay, they already asked what's the atomic radius across a period. So guys, again, when you see the question say across a period, the first thing you must think of is effective nuclear charge. And the first thing you see, and the first thing you do, the second thing you do, sorry, is to write down the formula. Guys, can I ask you all, right? When you all go across a period, what happens to the nuclear charge? Any idea? Okay, when you go across the period, what happens to the number of protons? It increases, right? Okay, so you must be very systematic by telling me the number of protons increase. So the nuclear charge also increases. Then what's next? If the nuclear charge increases, yes, okay, but we also need to look at the other factor that may affect the nuclear charge. So what happens to the number of inner shell electrons? Now guys, I ask you all, when you all go across the period, right? Where are the electrons being added to? The outer shell or the inner shell? You must only add to the outer shell, right? So that implies the inner shell electrons are the same. So let's write this down now. Okay, the shielding effect. Okay, if the number of inner shell electrons remain the same, the shielding effect will also remain relatively constant, right? Okay, so I need to write down these words over here. The shielding effect remains relatively constant. Do not ever tell me it is equal. Nothing is exactly equal. It's too absolute of a term. So you must tell me similar or relatively constant. Either one of these words works. So if the shielding effect remains relatively constant, then you must say what? As electrons are added to the outer shell. You add to the outer shell, which already implies the inner shell remains the same. But I want you guys to write down both ways. You can tell me about the outer shell, or you can tell me as the number of inner shell electrons remain the same. So you can tell me either the inner shell's perspective or the outer shell's perspective. Okay, so as you can already see, there's a lot more to explain when you go across a period. Okay, guys, I've discussed 2 factors. Okay, in this case, right, let's take a look. My nuclear charge supposedly increases. My shielding effect remains the same, so I'm just going to use a tick. So guys, overall, what happens to the nuclear charge? This one increase, this one stays the same, so effective nuclear charge must increase as well. Okay, so very simple. Now you need to come to a conclusion. Effective nuclear charge increases. However, as you notice, right, this is only the start of the entire explanation. Up until here, right, we only concluded the effective nuclear charge. We still need to link our way towards the atomic radius. Guys, what do you think the next point is? What do you think is the next relevant idea here? Any clue? Okay, what's the next idea in this question? If the effective nuclear charge increases, I already mentioned it's about how attractive it is, right? So it becomes more attractive. So what does that mean? Okay, so we write this down first. Okay, the attractions between the nucleus and valence electrons will increase. When it increases, finally, what's the idea here? It's about atomic radius, right? So if the attractions increase, then what will happen? Okay, it will pull the valence electrons closer to themselves, right? Because it's more attractive. So you just need to tell me that the atomic radius will increase. Now, just a little tip, right? To help you guys answer these questions even faster or think even faster. When you go down the group and across the period, right? I need you to take note. Usually the trends are opposite of each other. In fact, this is true. They purposely arrange it this way. You go down and you go across, the trends are always opposite. So if the atomic radius increases down the group, right, it's going to decrease across the period, and it's justified over here. Okay, it can be atomic radius, it can be ionization energy, it can be for everything that we're going to discuss. Okay, so that's for the first page. But now, before we move on to ionization energy, I want to now discuss ionic radius. Okay, because guys, you all need to visualize your head. We are going across a period, right? And when you go across a period, there are the cations on the left-hand side, and then the anions on the right-hand side. So we are going to now change this to ionic radius, and we're going to see, right, how to explain this pattern. Now for that, right, we're going to investigate period 3. Okay, this is a whole question that can carry out to 3 marks. So let's pay attention to the different steps. Okay, first, we have the cations on the left-hand side. But then on the right-hand side, we have all the anions. Now let's take a look. Between these two groups over here, let's check for a few things. Can you tell me how many electrons are there in the cations? Let me show you the proton number, 11, 12, and 13. So how many electrons are there? Over here. How many electrons? 10 electrons, right? Good. Okay, so if they have all 10 electrons, let me introduce another term to you guys. Okay, they are all isoelectronic. Isoelectronic means they all have the same number of electrons. You might want to use this term in your explanation, but if you don't, it's obviously fine. Can you tell me how many electrons are there on the anion side? So yeah, if I tell you this is 15, 16, and 17. How many electrons are there? Okay, good. So you can already see, right? Yes. Now that we are talking about anions, something is going to be slightly different. Also isoelectronic with each other. Can you all just do me a favor, right? For the 10 electrons, can you write down the electronic configuration first? Okay, like what we learned last lesson. Okay, how do you express 10 and 18 electrons? Can you give it? Okay, so shouldn't be that big of a deal here. 10 electrons is just 1s2, 2s2, 2p6. Afterwards, 1s2, 2s2, 2p6, 3s2, 3p6. So if you compare the cations and anions, okay, you can clearly see that they have different number of electrons. But let's answer this question first, guys. What is the overall ionic radius? Okay, so if you notice, guys, if you're going across the period still, you still need to use what way to explain your answer? You still need to use effective nuclear charge, right? So we talk about the first point. you all notice that the first point is the same as before? Okay, number of protons still increases, as you can see over here. So the number of the nuclear charge itself will also increase. Can you see that? Okay, so that means the first point is the same. Now we look at the second point now. How about the shielding effect? Shielding effect looks at the number of inner shell electrons. Can you all look at the inner shell electrons, right, and tell me, are they the same or different? Okay, I know the number of electrons now is a little bit same, right? Okay, since they are isoelectronic, you all agree that the shielding effect also remains relatively constant. Okay? So it's actually the same exact point up. Okay, the number of inner shell electrons still remain the same because same idea, whether it's anions or cations or even atoms, you're still adding electrons to the outer shell either way. It doesn't matter whether it's 10 electrons nor 18 electrons. You're still going to have the electrons added to the outer shell. Right? So the inner shell hasn't really affected anything yet. Later we will see an example, right, where the inner shell is actually affected. But for now, it's pretty much the same as before. So can you all see that the effective nuclear charge still increases? The attractions between nucleus and valence electrons still increases. So that means the ionic radius, guys, will also decrease, same as before. So pretty much, guys, a lot of in this topic, right, is a lot of repeated, recycled explanations, just for slightly different scenarios. So in this case, okay, ionic radius, I just want you all to take note of a very important word. Generally decreases. Please highlight the word generally in your answer and also in the question. They have given you these two words, right, for a very strong reason. Guys, what is generally? Why do they have to include the word generally? Okay, what does that mean? Okay, guys, if they never write the word generally, means what? The ionic radius literally just keeps decreasing, right? One after another, it just drops. But if they include the word generally, what does that usually tell you? Does it just drop straight up? Okay, usually there's a drop, maybe there's an increase, and then drop again, right? Okay, fundamentally, everything from the start to the end, there is a decrease, agree? Okay, or there's an overall decreasing trend. But then there's, of course, increases in the middle. Okay, so it's like how in real life you can see, like, you know, the economy. Okay, you will see the economy, right? Maybe go up and down, go up and down. But then let's just say overall it's still going down. That's the rough idea over here. Okay, so in this particular question, right, we're gonna answer the next part. Okay, why is there a generally decreasing trend? If it's generally decreasing, it implies there is an increase. There's somewhat of a sharp increase, right? Somewhere in our trend. Okay, it doesn't have to be sharp. Okay, but in this case, it's a rather sharp increase because I need you all to see how this works. Okay, in order to do this part, right, what I need you guys to do is to draw a graph. Right? Let's draw a graph like this, because you may be asked to plot this graph. And if you don't know your content, you're going to lose marks on the graph also. So over here, I need you guys to plot all the ionic radius. And over here, we're going to use Na plus, Mg2 plus, so on and so forth. Let's list everything down. Okay, something like this. Now let's see how we're going to explain this question. Okay, your job over here is to plot the points on the graph. Now guys, from sodium to aluminium first, what do you expect the trend to be? Upwards or downwards? It should be downwards, right? Because it's generally decreasing. So that's what we're going to do here. It's just going to decrease like that. Now you do not need to know exactly how it decreases. So you just decrease it anytime you want. Okay? So as you can see over here, it just drops. You can just drop it in a straight line. If it's not straight, it doesn't matter, obviously, as long as it's decreasing. However, guys, I want you to notice something. You have drawn two electronic configurations just now, right? Look at these two configurations. Now we are comparing across the cation and the anions. What do you all notice? Okay, look at the configuration. What does the anion have that the cation group doesn't have? Okay. Sorry? Okay. You notice that the anions have an additional of this part over here, right? Can you tell me what do they have an additional of? Additional quantum shell additional subshell or additional orbital. You must get your terms correct. Quantum shell, good. Remember guys, quantum shell is used the numbers to denote, right? 1, 2, 3. This guy clearly has a third shell, this guy doesn't, so that's quantum shell. As you can see, guys, if the anions have an extra quantum shell, do you expect the ionic radius to be bigger or smaller than the cations? Bigger. Because it's one additional shell, right? It's going to be larger. So that means, guys, when you want to plot your ionic radii for the last 3 guys, it has to be higher than the first 3 guys. Does that make sense? But overall, what's still the trend? Over here, it should still be decreasing. So that's why, right, I need to see this dropping as well. But the lowest of the anions must still be higher than the highest of the cations. Does that make sense? Okay, so make sure you all don't anyhow draw here. This one they will be very, very specific. Okay, you can join the points up together. Now, if you want to join from aluminium to phosphorus, go ahead, but usually I just draw this dotted line. Yeah, that's allowed as well. So notice, this guy is still higher than sodium plus, so that one is something you need to make sure. That just goes to show that one quantum shell does a lot of difference. Because it's physically speaking, one entire quantum shell difference definitely is going to be larger, a lot larger. Okay? So yeah, guys, this explains the word generally. Generally means, yes, you can still see they are going downwards, but then there's just one sharp increase. Our job is to explain why is there this sharp increase. Okay, so for your final mark in your question, right, you must tell me why. And it's very simple, because you can just explain it to me like what we have explained so far. The anions have an additional or an extra quantum shell. Since you have an additional quantum shell, it means you have a larger ionic radius, right? Okay, does this make sense? All right. So I'm going to show you guys the mark allocation for how this works. Okay. I thought the C now.
But you need to use us.
Really, man? Thought I'll put the.
Yeah, it's not talking about.
Okay, can. Wait, give me a moment. I'll finish this one. You what time need?
2:30, but they're late. So
Is it just for this week? Because this is a class I have every week. I thought I have.
I think it's really.
Okay. Okay, we finish this up first, then we kind of need to use the outside classroom for today. Okay, so anyways, guys, take a look up. Just highlight the keywords here. There's the idea of additional quantum shell. And let me show you all the mark allocation. This entire first part, right, to explain the general trend is only 1 mark. Yes. Okay, the graph, 1 mark. And then the final part over here is final justification, 1 more mark. So it's 3 marks in total. Now, if you'll be asking me, right, how come you write so much, you can only get 1 mark? Because in JC, right, it's not about how much you write, it's about how difficult it is to obtain a mark. Okay, so all this is very basic stuff. So that's why it's only total 1 mark. The graph is something that's a bit more challenging. Okay, that's why they allocate 1 entire mark to this. Okay, people normally lose marks in the graph. All okay so far? Okay, so what we're going to do now is to move on to our ionization energy, which is arguably a lot more important. Okay, but copy down whatever you need to copy first, because then afterwards we need to move outside. Okay. I'll just quickly get back to you. Did you say anything? Because yeah, she also never text me. You also don't know anything. Okay, no worries. That's fine. Anytime you're free, make it. Okay, so far I need this. Okay, I know issues are, we're just gonna move out first. Yeah. Okay, come, let's continue. Alright, so if you turn over to the next page, it's just more trends that we need to explain. Alright, so ionization energy is, I feel, the more important concept that we should be focusing on. In this case, we are still going across a period, but we are now talking about first ionization. Okay, so if you notice, right, sometimes, actually over time, the explanation starts to repeat itself. So you can start to write in point form, because I don't want you guys to spend too much time just writing again. Okay, so in this case, we are taking a look at across the period. We still need to discuss what? across they need to discuss effective nuclear charge, right? So effective nuclear charge is simply just this. We have to talk about each factor again. So before I write down anything, you guys can just write down in point form, right? When you go across a period, what happens to your nuclear charge? It still increases, right? So if it increases because of the number of protons, then same exact point like before. The other thing is shielding effect. Okay, same thing, right? You're still going across the period. You're adding electrons to the outer shell, not on the inner shell. So the shielding effect is just going to remain the same. And then finally, your effective nuclear charge is going to increase again. So let's just write out in point forms. Okay, nowadays when you write increase and decrease, right? Okay, maybe in our lesson we can just write using the arrows, so a bit faster. In exam it's not allowed now. Right, okay, but over here, you can just very quickly say that across a period, number of protons increase. Okay, so the nuclear charge increase, you'll use the symbol, go ahead as well, as long as you can understand what you're writing. Okay, then on the other hand, your shielding effect is relatively constant. Okay, because it's quite clear that the electrons are added to the outer shell. And then finally, you can conclude that your effective nuclear charge increases. But then this is where we need to slowly link towards what we're trying to explain, right? Okay, this is first ionization energy. So if the effective nuclear charge increases, what's the next important point? What's the next relevant point? The nucleus becomes more attractive, right? So we should mention the attractants first. Okay, so the attractions between the nucleus and valence electrons will increase. But once that happens, guys, what's the next relevant keyword to talk about? Remember, this is first ionization energy, which means we require the energy to overcome these attractions in the first place, correct? So that's why the attractions must be polar up with the word energy, like what I discussed in the previous lesson. Okay, energy required to remove an electron increases also. So first ionization energy increases across the period. It gets harder and harder to remove electrons. Okay, that's the idea. Okay, Ken? So you might notice, yes, you're writing a lot of things, but hopefully, right, by writing more and more, you start to remember more and more also. Okay, then you can just turn over to the next page. Okay, now, again, you can see that first ionization energy in the previous question, they use the word generally. I don't know if it's printed over there for you guys. Yeah, I think it is. Okay, so we try to write this down first. This is where things get a little bit more interesting. The first ionization energy generally increases because this implies, right, there will be certain anomalies that we need to discuss. Anomalies being, yes, that overall that's increasing, but then there will be some decreases. And our job is to explain what are these decreases. Why are there decreases when based on our explanation, it should be increasing, right? To make this easier for you guys when you study, right, I need you all to understand it's a lot better if you all remember for first IE where are the anomalies are. Okay, so if you take a look, it's from group 2 to 13 and from group 15 to 16. Okay, because when you go across the period, right, it's 1, 2, 3, 1, 2, 13, 14, 15, and so on and so forth, right? So you should remember these two groups first, it really helps. But take note now, guys, I tell you these numbers, it's only for first ionization energy. If you change this to second to third to fourth, definitely everything is going to shift, right? Because the number of electrons are different. So based on what I've just said, we take a look at the first anomaly now. All right. The first anomaly, I'm just going to use certain examples. Group 2 is magnesium, group 13 is aluminium, right? Now to facilitate this, right, I need you all to take a look at page 28 and just write down the electronic configuration first. Okay, over here, I'm going to introduce a rather new concept, which your school will also barely cover. Okay, but I want to cover more in detail. Okay. Okay, so write down the configuration for both of these real examples, and then from there, then we will discuss why is there actually a dip in ionization energy. Okay. Okay, so as we go on and on, right, you notice sometimes we need to write down the configuration to support our answer. So for example, over here, the first, 2 quantum shells, nothing much. Okay, but it's only here that it's a bit more important. Now guys, ionization energy, first IE is the removal of the first electron, agreed? So where is the first electron getting removed? In magnesium. Can you tell me where? Okay, 3s what? Let's describe this. It's a quantum shell, subshell, or orbital. Okay, you could say subshell. Okay, orbital is not wrong also, but okay, 2 electrons in the subshell, right? Okay, so over here you can tell me it's the 3s subshell that's getting removed, and I need you all to basically highlight this out. We are not really concerned about any of the inner electrons because I'm only concerned with the electron that you're removing, right? How about aluminium? Where is it being removed from? The 3p subshell, yes. So we highlight these two guys, and I want you all to notice, okay, why do you think, okay, anomaly means there are drops in the ionization energy, right? It doesn't increase. Why do you think it's actually easier to remove an electron from aluminium than from magnesium? Now, there are actually 2 answers to this. I'm going to go over the first answer, which is not that preferred. Then later, the second answer, right, is what normally you guys are required to write. Now, the simple answer is this. Can you tell me which one is further from the nucleus? 3p, right? So if it's further from the nucleus, is it less attracted or more attracted? Less attracted. So do you need more or less energy to remove? Less energy. That's why it is less than expected. Okay, that's the easy answer. You write that down first. So let me show you guys the phrasing. Okay, so the first reasoning is tell me that the 3p subshell is slightly further away from the nucleus. Okay, than the 3s subshell. Now, because of that, right, if it's slightly further away, you can tell me this. Thus, the 3p electron is less attracted to the nucleus and requires less energy to overcome or less energy to remove. Now again, right, I'm trying to make your answer as concise as possible, because this one only carries 1 mark. And 1 mark, honestly, right, don't write too much. Okay, I know just now there was a long ass explanation that is only 1 mark, but now we have no choice, we can't shorten that. That's the shortest already. Here we can make things shorter by telling me this, slightly further away from the nucleus, yes. But the 3p electron, so you all can use this word, 3p electron is less attracted to the nucleus, that's why less energy. Just highlight these keywords, as long as they have these, right, then your answer won't be too long. But now let me introduce another idea, and we're going to talk about energy. Energy is an idea that comes in a couple of chapters time that will be tested in mid-years. Okay, but let's use this second reasoning, which is a lot more appropriate, I guess. It's a bit harder to digest, yes, but I will explain a little bit more. Okay? Now, same idea, guys. 3p and 3s, right? Different subshells where you remove the electrons from. Now, I want to introduce this idea called an energy level diagram. Now, what's an energy level diagram? Okay, I want you to take note. You see all these electronic configurations, right? We are going to list down what amounts of energy these subshells have. Right, let's start off with 1s. 1s is very close to the nucleus, right? Where do you think it will be? Do you think it's very high energy level or low energy level? Okay, actually it's very low. Okay, let me introduce some ideas to you guys now. What is the idea when it comes to energy levels? Okay, let me give you guys some rules first. We haven't learned these rules yet. We'll talk about it again in a few chapters time. But go write this down. When you have a low energy level, can I ask you guys, do you think you're more stable or less stable? I want you to imagine a little kid. Now, this little kid, right? Imagine he's hyperactive. Imagine he has a lot of energy, high energy level. Do you think you can control that kid very easily? No, right? He's running about, jumping around, then you're like very tired, right? He's very stable or unstable? Very unstable, right? So electrons work the same way. Electrons are like that hyperactive kid. If they have a lot of energy, high energy level, that makes it usually very unstable. On the other hand, guys, sometimes you know the kid play around already, right? Play for a few hours, then get very tired, correct? Then he wants to sleep. In that case, he has run out of energy, so do you think he's stable or unstable? Okay, very stable, very easy to control him, right? Okay, so it's the same idea when it comes to chemistry. Okay, energy levels in chemistry, right, have a correlation to how stable the compounds are. Okay, now that I've told you guys this, can I ask you, a 1s electron, is it very stable or unstable? Think about it. 1s is super close to the nucleus, right? So do you think it will very easily move around and jump around? No, why not? Why does it not like fly around and shit? Why is it like staying over there? Because it's very close, so it's very strongly attracted to the nucleus, right? I'll talk about all this again, okay? So I want you to look at the thought process. A 1s electron, very close to nucleus, and because of that, it's very strongly attracted to the nucleus, right? Now, if you're very strongly attracted, that means you're not going to like flail around and then like jump around. The electrons are basically going to stay there. It's a very stable electron. An electron that's very stable has high or low energy level. Low energy level. So guys, I'm trying to make you guys see the connection. This is basically a train of thought. Go and write all this down because this will help you see, right, one thing leading to another. 1s, very close, it's super tightly attracted, it's going to be very stable. Stable means low energy level because this is something that I just taught you guys. So the only new part is over here. All these are all common sense, logical. So guys, from now on, you may be asked to plot an energy level for all these configurations, all these subshells. The 1s subshell should be at its lowest, right? Guys, you think about it. How do you think it's going to proceed from here on out? The next guy, 2s, then 2p, then 3s and 3p. In relation to the nucleus, does it get further or closer? Further. So you think about it. If it gets further from the nucleus, that means it's going to get, come follow me on the train of thought, less strongly attracted, right? If you're less attracted, that means what? Are you stable or unstable? There's a higher chance for you to like just like, the electrons fly around, right? So it is less stable. Something that's less stable has high energy level. So that's why as you keep going further away from the nucleus, you start to get higher and higher energy level. So it's just going to get higher from now on. Can you see that so far? But I want to give you another detail. From 1s to 2s, can I ask you, is the jump in energy very large or very small? I repeat my question. Yes, it increases. But from 1s to 2s, is the jump going to be very high or just a slight jump? Think about it. Why high? Good. It's a quantum shell jump, right? Based on the number. And because of that, I need to see a rather huge increase in quantum shell. Now, this line over here just represents the level. Okay, because after the line is done, right, you all can actually draw your electrons in the spin state. You know the electron box. You can actually fill it up over here as well. So that you learn like configuration, you learn electron in box, but then next time you all will learn energy level. I think RI will teach this quite early, that's why I'll tell you all this now. Okay, I think it's very useful. Okay, so I don't put the electrons there yet. That's not my point. Guys, from 2s to 2p, is the jump going to be larger than this or smaller than this? Why? Because it's what jump? It's not a quantum shell jump, right? It is now a subshell jump. So comparatively, guys, I need to see a much smaller gap as compared to this. Don't need to measure, just make sure agar looks very obvious. Guys, how about the next one? 3s. What does that mean? 3s, quantum shell, way larger jump. Then afterwards is 3p already, right? Okay, so that's the main idea here. In chem bonding, basically the next lesson, the first lesson, I'll come back to this idea. Okay, this will help us understand why some elements can hold more than 8 valence electrons, like what I showed you guys during the trial lesson. Okay, so you all need to understand this first. I'll come back to this eventually. But for now, I just need you all to ask me to just just tell me something. 3p and 3s, come back to this particular question. 3p has a higher energy level than 3s, right? So can I ask you all, if you have a higher energy level, do you need more energy or less energy to remove that electron? Less. Why less? Because I already explained here, right? The higher the energy level, the less stable the electron. so it's less strongly attracted. So you need less energy. So you see this thing over here very useful. Whenever you're lost, just come back to that. Okay, so let's write down the second explanation, which is what you are required to write up. Okay, the 3p electron has a higher energy level than the 3s electron. And because of that, thus, you can just go straight into energy. Don't need to tell me about less attracted. The 3p electron requires less energy to remove than the 3s electron. And that's why you can just tell me immediately that your first ionization energy of aluminium is less than the first IE of magnesium. I want you guys, when you all do the tutorial, right, I don't want you guys to use the first explanation. I know it's a lot more intuitive, right? But a more matured answer will be to talk about energy levels. Because eventually, we're going to learn energetics. And I already showed you guys during a few lessons ago, energetics is a topic tested in the exams. And you need to understand this idea first. Okay, it's a fundamental chemistry idea. It's not an atomic structure idea. This is fundamental in chemistry. Okay, so very important idea here. Any questions so far? Okay, all good. Okay, so that's the first anomaly. Okay, so now we can probably speed things up by looking at the second one, right? So I need you guys to now turn over to the next page. I've already now discussed group 2 to 13. Now we're going to discuss group 15 to 16. So same thing, guys. I want you guys to write down the configuration for the elements. So we discussed, let's see now. Okay, we discussed phosphorus in 15 and sulfur in 16. Okay, go write down the configuration first. Okay, let me see what's up with this. Okay. Okay, slightly different explanation. You will see why. Okay, it's not because I say different explanation, so it's different. Okay, no one. Okay, there's a way to know one. Right, okay, so let's see. Right, okay, so we take a look. Just keep on listing out everything. Okay, now once again, guys, who are we concerned with? Do we care about all the electrons here? No, right? We are only concerned with the electron you're removing from the outermost shell. So guys, go and highlight the outermost shells first. Okay. Now, can we use the previous argument over here? 3p has a higher energy level than 3s. You notice they have the same energy level, so we have to look for a different explanation. Okay, we know that it's actually easier to remove an electron from S than from P. That's what scientists figured out. Okay, they realized, hey shit, why is this so much easier when we predicted it to be harder? So what do you think is an explanation we can find in this case? Okay, in the question, right, they say, hint, draw an electron in box diagram. Okay, I'll draw the electron in box diagram. Okay, but first, I think you see the notes. They say, draw an electron in box diagram for the outer quantum shell. So what do they want you to draw? Come, tell me. Okay, if they ask for outer quantum shell, they want us to draw who specifically? 3s only and 3p, right? Because quantum shell is a number. Okay, good. You all understand your terms. But do I really care about 3s? Okay, no. So I think let's change the instruction a little bit. What should we change our instruction to? We only care about 3p, so what's the instruction here? For the outer subshell. Good. Outer 3p subshell. So sometimes, right, it's very important to understand these terms so you know exactly what we want. Okay, we just change this a little bit. Okay, so outer subshell, 3p. So let's draw it. Okay, just give it a draw. You can draw it like this side, like that. Don't need to draw everything else. Okay, just draw the subshell. Okay. Okay. Right. Okay, remember electron in box diagram. What does the box represent from 2 lessons ago? Okay, a box represents an orbital. 3p, how many orbitals must you draw? Okay, 3. Okay, so I only want to see 3 boxes here. 3 boxes, 3 boxes. Okay. So 3 electrons, remember, electrons want to fill up the seats by themselves first. It's only 3p4, then suddenly one guy is like, okay, I have no choice, I have to sit with this random guy. Can? Okay, what do you notice? Why do you think it's easier to remove an electron from sulfur than from phosphorus? When it's meant to be harder, actually. Why? Okay, so nothing to do with stability here, because once again, they are both in the same like energy level, right? So we can't use that energy explanation or stable explanation. But remember the bus analogy. You know, they like to sit by themselves, right? And then suddenly you need to sit with someone else. Now imagine you're sitting with someone else, right? Are you more willing to leave your seat or less willing? You're more willing to leave your seat whenever possible, right? So guys, what will electrons face whenever they are sitting together? Remember, electrons, whenever they are together, they will face repulsions, right? That's why they have to put themselves singly first to minimize the repulsions. Since there's repulsions here, and there are no repulsions here, or less repulsions, it'll be easier for you to remove, right? You can just less energy required. So that's the answer here, but I need you all to be very specific in your explanation. A lot of people just tell me, okay, there's a lot of repulsions. But where? There's repulsions everywhere, right? You must specify exactly it's in the 3p subshell. So in the 3p subshell of sulfur has a paired electron. Okay, you must specify, bring up this point first. It's because he has a paired electron while the phosphorus doesn't. You can then tell me which experiences inter-electronic repulsion. Now guys, just take note. If you just tell me sulfur has inter-electronic repulsion, you're just stating the obvious. Because there are paired electrons everywhere. 1s2 is paired, 2s2 is paired, 2p6 is all paired. So it's not specific enough. Okay, you must tell me it's the 3p. That's why I keep asking you guys to highlight whatever subshell that's relevant. Can clearly see from this diagram. Because it experiences inter-electronic repulsion, less energy, always talk about this, is needed to remove an electron from sulfur. Done. Keywords, specify where the subshell, whose subshell, there's a paired electron, and then finally inter-electronic repulsion, finish. Cross energy afterwards. Okay, any issues over here? So notice, just on ionization energy alone, there's so many anomalies. Okay, but then when you move over to like second IE, right, of course it won't be the same groups anymore. Okay, that's why some questions can be a bit hard. So any questions? You guys? You're doing okay? Okay, we're just gonna finish up a couple more pages. Things like 5 more pages. Okay, so take a look at page 30 now. Okay, we're gonna learn this thing called transition elements. Now let me tell you what's required first. On page 30, again, you all know what transition elements are? Okay, basically transition elements are from your scandium all the way to zinc. Okay, now this isn't entirely correct, but it doesn't matter now. Okay, guys, I need you all to know something. The definition, you don't need to know yet. Okay, you can basically ignore the definition until J2, until the last topic of J2. There's a high chance they will not test the definition now. Okay, they only test it after you learn transition elements. What you need to know though are the trends. So guys, this trend is across or down the group. It's going across a period, right? Okay, so if you're going across a period, what do we explain? How do we explain? We must go back to our idea of effective nuclear charge, right? Okay, so it's the same idea. Okay, so we do the same thing, but again, we do it in point form. Okay, so to explain this, right? Okay, actually, before we do anything else, I want you guys to practice writing a few configurations for transition metals. Okay, and it's relevant in our explanation. I'm not asking you all to write fun. All right. Okay, so I want you guys to write down titanium, scandium, and manganese. Now we are like going across the period here, 22, 23, 25, right? don't take econs. Oh, you don't, right? You take history. You take econs? I'm just reading that. My gosh. Freaking flashback. Yeah, you'll be doing that like soon. You know that is in J2. You guys are learning demand and supply now, right? Like have you even started econ stuff? Yeah, the classic demand and supply stuff. Okay, guys, you notice, I remember I told you guys the short form. Okay, I'm going to use that short form over here because the first 18 electrons, right, you can compress it into argon's configuration. So it's just argon. What I'm concerned with are the following. So after argon, what do we have? It should be 4s2 first, right? Then this is 3d2. Okay, then 4s2, 3d3, 4s2, 3d5. Okay, so we are I gave you a few examples here, but the idea is going across a period, right? Okay, now that we answer the question again. Okay, effective nuclear charge is nuclear charge minus shielding effect. Can I ask you all, what happens to the nuclear charge? Okay. Nuclear charge must increase because you are still increasing protons, right? Okay, how about the shielding effect? Shielding effect must look at the inner shell electrons. So what happens? Same? Guys, what is the inner shell in this case? Okay, 4s is the outer shell, right? The inner shell is now considered 3D. Now, do you notice over here, you are actually adding electrons to the inner 3D subshell as you keep going across the period. So what happens to the shielding effect? Now the shield is becoming more and more congested with electrons, right? So what will happen to shielding? Increase. More electrons blocking or shielding from the valence electrons. So here, your shielding effect actually increases as well. So let's write down the explanation so far. Across a period, okay, you can write down a short form if you want. The number of protons increase, so the nuclear charge increase. Okay, but let's write the full version for the shielding effect. Here you can tell me a shielding effect actually increases, because in this case, I hope you all notice inner shell electrons. Okay, you can tell me two ways. As the electrons are added to the inner 3D subshell. So be very specific, inner 3D subshell. 3D is not on the outside. So you specify that. Okay? Hey guys, can I ask you all what happens over here? If nuclear charge increase, shielding effect increase, so what happens overall to the nuclear charge, effective nuclear charge? Okay, it's like cancelled out, right? So yeah, it remains the same. So you can now tell me that the effective nuclear charge remains, can you use the word same? Okay, it's never really the same. It's relatively constant as the increase in nuclear charge is offset by the increase in shielding effect. Okay, you can write this sentence inside, but I think if you don't, it's honestly not that big of a deal. Okay, this is kind of like an optional sentence, kind of to boost it a little bit more. I'm not sure whether your school will require this because some schools do require it, some schools don't. And it's honestly not that important. Okay, so you can consider the word offset, right? Hey guys, because of that, can I ask you what happens to the atomic radius? If the attractive strength of the nucleus remains the same, so what? Does it have a trend, increasing or decreasing? No, right? Okay, so immediately here you can end off your answer. Don't need to tell me about attractions and whatnot, because if it's the same, right, there's not much more for us to discuss. You can now say atomic radius remains relatively constant. Right? Oh, need can. Okay, nice. Okay, your copy this. Go in. Okay. Okay, all good so far. Right, let's move again. Okay, so if no issues, right, we're just gonna very quickly finish this up. There are some application questions at the back which are quite important. Okay, but one thing I want to discuss, if you look at the next page, right, I hope you realize that by now, atomic radius and ionization energy recycle the same explanation. So for page 31, right, you'll just write there, refer to page 30. It's the same exact thing. But here, instead of atomic radius, it is ionization energy. That's it. Okay, we don't waste time for page 31. Okay, I want to proceed over to something that's more important, which is page 32. Okay, so just make a note to self, and then we go to page 32, where we will discuss this thing called successive ionization energies. Can someone tell me in simple terms, right, what does successive mean? You all know what successive means? Okay, successive just means one after another. Now remember, guys, ionization energy, right? How many electrons are you always removing in one go? One only. So first IE means you remove the first electron, second means the second electron, that's it. One at a time. So that's why ionization energy can be measured successively. So guys, look at the first question, right? It says right there, successive IE increases. So can I ask you, does it get easier or does it get harder when you remove electrons? It gets harder and harder, right? We need to understand why. There are two ways to explain this. I'm only a fan of the second way, but let me show you guys the first method, which you guys might prefer also. Okay, but first, guys, okay, let's just very quickly, right? Write down the equations for first, second, and third IE. Okay, I remember emphasizing on this. This is very important. Okay, the way to look at ionization energy. Okay, so it should be quite okay. So remember, I need you guys to include the gaseous state symbols. Okay, because this is the first one, right? Okay, you remove, they get a cation ion, then so on and so forth. Now remember telling you guys another thing as well. When you remove an electron, what species am I concerned with? Do I look at the species on the left or on the right? Okay, the right, sure. Remember, where are you removing the electron from? From the guy on the left or from the guy on the right? From the left. So I need you guys to always highlight the species on the left one. This is basically our concern here. In this question, we are trying to understand, right? Why does it get harder and harder to remove electrons from this guy? That gets harder to remove from here, then even harder to remove from here. Okay, so later we will see another version of this. Let me show you guys the first way to explain this, guys. The first way is by using effective nuclear charge. Whatever that you're familiar with, we apply to here as well. So take a look, guys. As you remove electrons, can you tell me what happens to the nuclear charge? Okay, as you keep removing one electron one after another, what happens to the nuclear charge? Think of it. Good. Why remain the same? Because are you removing protons? No. So in this case, the number of protons remain the same, so nuclear charge also remains the same. Can I ask you the second question? Your shielding effect. So remove more and more electrons. What happens to the shield? Weaker, right? Okay, there's less shielding. So there will be lower shielding effect. But I'm not a fan of this explanation because if you recall what I said, shielding effect is dependent on what? The number of inner shell electrons. Now guys, when you remove electrons, you remove from the inner shell or from the outer shell? Outer shell. So guys, do you notice a little more with this side? You have an outer shell and then you have an inner shell. When you remove, okay, let's just say there are two electrons on the outer shell, right? You remove the first one and you remove the second one. Does the number of inner shell electrons change? No. So that's why I'm not a fan of this experiment. But apparently, right, this is still part of the syllabus. So you can use it if you want. But later, that's why I'll show you guys something that's a lot more convincing. That's why I prefer that one. Okay, but anyways, let's just get this out of the way first. What happens to the overall effective charge? It will increase, right? Now then we just explain our answer. So you can tell me number of protons remain the same. So the nuclear charge also remains the same. Afterwards, we have shielding effect. Shielding effect decreases. Okay, then you can just very quickly tell me it decreases as more electrons are getting removed. Okay, again, I'm not a fan of this because you remove the outer shell electrons, not the inner shell electrons. That's why I think this is a little bit. Do you agree with me on this? Okay, a little bit weird, right? Okay, never mind. Okay, and because of that, the effective nuclear charge increases. Hey guys, is it harder or easier to remove now that you have a higher effective nuclear charge? Harder, right? Because the attractions between nucleus and valence electrons, or whatever that's left, is now higher. And since it's higher, more energy is required, right? Okay, so the successive ionization energy increases. It is an acceptable explanation. You can use it if you want. Okay, if you don't really give a shit, right? And then you just want to score marks, right? Yeah, go ahead. Okay, but I feel that the other version, right, will carry on to future concepts better. So since this, okay, I'll tell you guys this second version, which I feel that it just has a lot more applicability in the future. Okay, so write this down first, then I'll explain the logic of the second one. You guys might prefer it as well. Okay, any issues? Okay, to remove any doubt, right? Okay, come, let's take a look. I highlighted all these other species here. I want you to think of it from a more logical point of view. Okay, not really like effective nuclear charge, where you can't really see anything. Okay, I'm going to remove an electron from X, the atom, right? I require energy because I'm trying to overcome the what? Attractions between the positively charged nucleus and the electrons, right? Okay, settle. But guys, you look at this, I'm now trying to remove an electron from a cation, not a neutral atom, from a cation. Can you see why it's more difficult? Because now it actually has a positive charge. Can you see that it has stronger attractions with a negatively charged electron? So you need more energy to remove. Guys, you don't believe me, or you keep on going. Now the charge upgrade to 2 plus. Is it more attractive or less attractive? More attractive, right? 2 plus and electrons will have more attractions. It's going to get even harder to remove. And as you remove more and more and more, x2 plus, 3 plus, 4 plus, 10 plus. Guys, 10 plus, do you think very easy to remove? No, because 10 plus charge is so attractive that it will hold the electrons back very, very strongly. Does that make sense? Okay, so how do you phrase that? I'll show you guys, but you all just need to understand what I'm saying first. Okay, so anyways, what does that mean? You all can just say this. It becomes increasingly difficult, okay, to remove an electron from an increasingly positively charged species. I use the word species and not like cations or atoms, because here the atom then suddenly become cation. So overall term that is better to use, more versatile term, is the word species. Okay, not done yet. Okay, so it's increasingly difficult to remove from an increasingly positively charged species. Thus, the energy needed. Okay, we add on a bit more. It's increasingly difficult due to the stronger electrostatic forces of attractors. Or I can just say due to the stronger attractor. Okay, that's why you need more energy to overcome. Okay, thus energy needed to remove successive electrons increases. So there's not really a keyword here to highlight. It's just an overall package. It's just a sentence. Okay, so you can use this way to phrase. Please take note of this. Rather you guys use this, right? Because in future, when we look at further topics, we will come back to this idea. Okay. Any issues so far? So I personally think that this answer is a lot more convincing. Okay, so we're gonna write this down. Hey guys, we are pretty much at the end of like content already. Now we're gonna ask ourselves, right? Okay, this guy needs a certain amount of energy, maybe like 500 kilojoules. This one 900 kilojoules. Some 1000 kilojoules. Okay, but it doesn't really matter, right? Everything's gonna keep increasing, right? Because that's what we explained. It keeps increasing. It just gets harder and harder to remove electrons. So what the hell is the point of studying this? So let's look at the page 33. The point of doing this, right, is that we can actually find out an unknown element's identity. By removing electrons one by one, we can actually determine who that element is. It's quite impressive. Okay, so let's see how this works. Okay, so look at the graph. Just look at the graph. Okay, don't need to do anything, just look at it. And can you tell me, right? What do you look at? Okay, that's my question. What do you look at? Okay, the graph's so big, right? But you must know what to pick up. What is the most striking feature of this graph? Okay, the increase, everything's increasing. What? Can we be more specific? The sharp increase. Okay, good. So guys, take a look at this graph here. It doesn't matter, right? All the numbers are here. There's no math calculations, whatever. 1, 2, 3, 4, 5. And suddenly there is a very sharp increase. And then 6, 7, 8. Okay, sure. Okay, so from the 5th to the 6th electron, there's a very sharp increase. So what is that? Guys, remember what we're trying to do here? What did I just say? We are using this to determine an unknown element. What is his identity? Guys, how do you identify elements? How do you identify elements? Okay, now there are groups, right? Okay, what do the groups normally represent? The number of valence electrons. So do you notice, guys, when you remove electrons, right, you start from the valence shell. So do you see the connection here? If I know how many valence electrons I remove, I know what group he's in, then it narrows down the possibilities, right? So guys, to determine the identity of an unknown element, I basically have to find out how many valence electrons it has. Because the valence electrons can be tied to this group number, and you can then find this identity. So guys, yes, the graph, the only useful feature is a sharp increase because everything else is increasing one, right? Can you tell me what you infer from this? How do you know that? Okay, there's an explanation we need to write out, so we can't just say 5 valence, right? Okay, the 6th electron is a lot harder to remove than the 5th electron. Can you tell me what does that mean about the 6th electron? Different shell. To be more specific, how different? Outer different or inner different? It's inner shell, right? Okay, so guys, let's write it. I'll answer down now. Our answer is split in parts, very short and sharp. So the first part of your answer, you just need to tell me there's a sharp increase in sharp increase in ionization energy from the 5th to the 6th electron. Basically, the first thing that you tell me is the data from the graph, the surface level data. Afterwards, you tell me what it means. This implies it's so much harder to remove the 6th electron. So that implies that the 6th electron is in the inner quantum shell. Now use the terms that we have learned now. Okay, don't just say inner shell now. Okay, let's make it more complete here. Okay. Inner quantum shell a lot closer to the nucleus, a way harder to remove. So if the 6th guy is on the inside, how many were on the outside? 5 now, right? Okay, that's simple. Okay, so hence it has 5 valence electrons. So that means it's in group 15. That's our answer. So it's actually useful. Okay, this one we haven't learned for nothing. Because a lot of the times in real life, right, we need to determine what the hell we just obtained. Like you just dig out the ground, then suddenly got one element, right? Okay, we need to know what it is, man. Okay, so this is how they figure out. Okay. Okay, any questions? We are pretty much done with the chapter already. All you guys need to do, right, is to look at the next page, that question. I just need you all to try the same thing. But for this next page, on page 34, they want you to identify the element Not just the group, but the actual element. So I'll leave it to you guys first. Do whatever that I've taught you guys first. Okay, I'll talk about the graph in a bit. Okay, try to write an explanation for that also. Okay, but actually, yeah, maybe you all can write later after I confirm the answer. Okay, but come, let's look at this graph first. Okay, where is the striking features or feature in this graph? Okay, where is it? Yeah, sorry, 1 to 2. Okay, so 1 to 2, right? Okay, there's actually a reason. Actually, that's not the largest jump. There's something even larger actually, which is 3 to 4. Okay, so sometimes we need to compare and contrast to see which one is the most striking feature. Yes, there's a slight jump from 1 to 2, but that one later we'll discuss. Okay, so perhaps maybe the graph is a little bit old, because you can see it looks a bit old. Okay, that's why maybe it's a little bit blur. Okay, but don't worry, nowadays your exam, right? All the questions will be very, very straight, very, very like clear. Okay, no worries. Okay, but is that the only sharp jump that you notice? Is there another sharp jump here? From 11 to 12. Okay, guys. So clearly there's another sharp jump. But I can safely say, do we need to care about this? Guys, I'm trying to determine an unknown element's identity. And for that, I need to look at the group number, which is tied to its number of valence electrons. Guys, valence electrons, do I have to care about these two? No, they're not even the valence, they're on the inner side of the electrons really, of the atom, sorry. So it doesn't matter. So you need to know which data to pick out here, because it's one of the first few electrons removed from the outside. So that's all that matters. So just based on this information alone, can you tell me, right, which group it belongs to? The sharp increase in IE is from the third to fourth electron, implying that the fourth electron is in an inner quantum shell, implying that it has 3 valence. It's in group 13. Can you see that first? Okay, but that's not it. They want us to determine who exactly from group 13. So can you tell me, right, what are some possible options? Okay, you can take a look at the data booklet. Okay, but if you don't have a data booklet, okay, let's take a look. I'm gonna give you guys 2 options. Your group 13, right, will look something like this. Boron, and then afterwards it's aluminium. You won't really discuss anything below aluminium lah. Okay, everything else is a little bit bigger already, like gallium and all that. No lah, not very commonly tested. Can you tell me, right? Okay, can it be either one of them, or is it definitely one of these answers? Why can't be the first one? Okay, you remove more than 5 electrons, right? Okay, also definitely the answer in this question is aluminium, because you remove 13 electrons in total. Okay, even though you've gotten your answer, I want to explain certain other ideas as well. Okay, so can you take a look? Over here, we have so many electrons being removed. Okay, so let me fill in a few numbers. Aluminium has 13 electrons, and just nice over here they have removed 13. But you want to take note, not all the time, right? They will show all the electrons being removed. What if there are 28 electrons? Then they only remove like 13. If not, your paper will have like 28 electrons, which is a lot lah. Okay, so that's why they don't draw too much. Okay, but I need to relate, right, to the graph over here. Now, as we all know, right, guys, aluminium's electronic configuration is 1s2, 2s2, 3s6, 3s1. I'm sure you guys can draw this yourself. Wait, sorry. 3s2, 3p1. Okay, so I'm pretty sure you all can draw this, correct? Okay, and the idea is that how do we relate this to over here? Can I ask you all right? This first electron is a very subshell. Okay, good. So let's annotate our graph. This is in a 3p subshell. Then how about these two? They are removing from the outside in, right? So it's basically everything backwards. 3s2. Does that make sense? Now I need you all to notice, right? Why is there a slight jump over here? Because now you can see 3p and 3s. It's a slight subshell jump, right? That's why the jump over here is actually not that significant. If you would tell me that this jump is the main feature, right, then you would have told me a completely different model, a different apple. Okay? After 3s2, why is there a sharp jump? Because 3s to 2p is a subshell, is a quantum shell jump to 2p6. 2p6 meaning p6 electrons here, right? After 2p6, it is 2s2 here. Now, guys, by right, what did you actually see here? Maybe the graph is a little bit old, but by right, what should we do here? There's a slight jump. Yeah, I know there's like no jump over here, but okay, maybe it's not that significant, but maybe you can show a little bit, not too much. Okay, then afterwards, guys, why is there a huge jump from 11 to 12? Because it's 1s2. It is the closest to the nucleus, so you see a massive jump also. But again, as you can see, this is not helpful to identify the elements identity. So that's it. Okay, it's good to relate to the graph also. Any issues so far? Don't have, huh? Okay, if you can take a look at the last page, right? It is a similar question type, but instead of graph, it is numbers. Okay, so once you're done with this, you can flip over to the last page. Okay, this one, right? I don't need you all to write down the explanation 3 times. I just need you all to just do the question. So just tell me which group is in Canary. As long as you can arrive at the correct answer, we shall just move on. Explanation wise, I've already covered. So look at the last page, just try these questions. Okay, instead of a nice diagram, they give you numbers. Right? Okay, any issues? Okay, what's the first question's answer? Group 15. Okay, then the second one is group 14. Okay, any issues? Well, okay. Okay. Right, nice. Okay, so numbers, you all can see which one is the largest jump, but it's not going to explain. It's child's play. Okay, if there are no questions, I have picked out some tutorial questions for us to try till the end of the lesson. But we take a short break first. Okay, and then we continue in a bit. Okay, 7 minutes until like 3:40, then we come back. Right? Okay. For the last 20 minutes, we're going to try a few questions. I already have a few in mind already. Okay, we're going to start a bit easier, then we go towards the harder questions. First question, okay, let's just give this a try. Okay, MCQ question, generally I only allocated 2 minutes. Okay, but because you guys just started, I'm going to give you guys 4 minutes. Okay, 4 minutes, see whether you can come up with an answer for this. Okay, so by 3:46, okay, try to get an answer for this. Six, level 1, question 1. It's MCQ, it doesn't matter how you do it, as long as you have a very fast technique, go ahead and use. MCQ is all about speed, it's all about efficiency. Later I'll show you my way of making things fast. Okay.
You guys have about 1 minute left. Sorry, no, 2 minutes left.
Okay, I've got an answer. All right, okay, so let's take a look at what the answer is. Answer is A, not C. Okay, so let's see how this works. Okay, you see, exam questions, right? You are really under the pressure of time. So sometimes, right, the way you think, right, might be a little bit compromised. It's fine. Let me show you guys, right, how to make this as efficient as possible. And there's a way, right, to consolidate all this data into something that's a lot more easier to process. Okay, notice, guys, this is an angle deflection question. I'm pretty sure you guys can identify the question type right off the bat. Protons deflect by positive 15 and all that, yes. Okay, but I want you guys to remember, take out this relationship. We have to consider both factors, both the mass and the charge. Now take a look. Protons are just protons, right? It's just one proton, deflect by positive 15, yeah, okay, sure. But you have an unknown particle X, you can already see, right, 3 times less deflection. So immediately from this information, right, what could this tell you? Could this mean it is heavier? Possible, but it's not definite, right? Because there's also charge. The charge could be bigger or smaller? Smaller. Okay, notice smaller angle of deflection could mean smaller charge or larger mass. Could be both. I really don't know. So we need to account for both factors. How do you account for both factors? Let me teach you all. Next time when you all see protons, neutrons, electrons like that, right? This is very messy. We need to consolidate it into one item. How? Option A, guys, we have one proton, right? So the proton number is 1. Neutron number is what? Neutron number, sorry. Mass number here is 3. Guys, is there a charge on this compound? What's the charge? Minus, yes, again, -1, minus, because you have 1 extra electron compared to a proton. Can you all very quickly do the same thing for all the other 3? Okay? By doing this, I can tell you all, it is a lot easier to see your data. Okay? Right now, it's very, very congested, and I hate it. But okay, you also need to know when to consolidate data, right? Okay, they give you protons, neutrons, electrons, you might as well just put it into one thing, you know, right? Okay, so anyways, okay, as you keep on doing, okay, go and check your answer is 2, 5 minus. Option C is 3, 6 minus. Option D is 4, 9, 3 plus. Guys, is there an option right now that I can eliminate? D. Because D, we know protons are positively charged. So if it deflects in the opposite direction, X must be negatively charged. Preliminary option we can cancel out is, we have 3 options A to C to consider, they're all -1 charge. Guys, what can we do now? Guys, remember, we have the exact angle of deflection that we need to find, correct? So take a look, what is the angle of deflection for A? Let's take a look. Okay, now what we can also do is this. Protons we can also express in this format. Okay, protons you can even call it like P, and then what's the proton number? 1, right? What's the neutron number? Neutron number is also 1, right? Neutron number is protons plus neutrons, so there's only 1 proton, so you might as well put it there. What we can do now is to express everything in this version. So I can also use the calculation method because there's some calculations needed, and I told you guys you must convert it into the K version. Use this if you want to. Let's calculate for protons first. Angle of deflection of protons is 15. K is, don't know. Q over M is 1 over 1. Can see that? So in other words, based on this information, we can find that K is equal to 15. Once we know K is 15, we can recycle K for the rest of the purposes. Okay, so over here, angle of deflection of A is what? A is 15 times. Can you tell me what's the charge over mass of A? Okay, good. -1 over 1, which is negative. Oops, my bad. -1 over 3. Okay, so you can get -5 degrees. That's why this is the answer. Calculate for the rest. Okay, very quickly, and this is the most efficient method. 15 times, what's the charge here? Over mass. Okay, look at the charge, don't look at the protons. -1/5, you get -3 degrees, that's wrong. Angle deflection of C is 15 times. What's the answer here? -1/6, answer is -2.5. And even if you calculate for T, you'll realize something. Can you calculate for T also? What's the charge over mass? +3/9, right? You will get the correct magnitude but different direction. So this is still wrong. It's the fastest already. Okay? So I'll tell you some tricks and all that you can use for next time. Okay, let's very quickly proceed to another question. Okay, let's go all the way over to level up question 1. Level up, we need to go to other questions. So the NJC 2018 prelim, level up question 1. You see like that graph over there, yes? Okay, correct. Go over to that page. If I'm not wrong, it's page 14. Is it? Yeah, okay. Now, if you guys need paper, I can give you guys as well. Okay, but for now, what I need you all to try is just part 1. That's all we're going to do today. Because part 2, you can find from the notes. No point for me to do that here. Okay, try part 1. Okay, I need to see some sketches. Okay, explanation, you can try a little bit. Don't need to write too much here. Right? Okay, this is testing on your trends of whether you know the trends or not. Right? What is the 2 points? Okay. We will explain the answer together. So I just need you all to plot the 2 points. Okay, so then afterwards we can just straight away go. Alright. Okay, so I think we can just go through now. Okay, it's good to identify what are the elements first, because they're all consecutive, right? So you can check your periodic table. And what's before magnesium? Sodium. What's before sodium? Neon. Right, okay, so we have sodium and neon. You can refer to the periodic table as well. Now I see that you guys have drawn like this, right? Okay, why? Let's explain. Why is it sodium and why is it neon? Because guys, what's the direction over here? Are we going down the group or are we going across the period? Across the period, and generally across the period, first IE must increase, right? Now, in this case, increase means again like that increase, right? However, this is the wrong answer. Okay, let's try this again. Yes, your sodium, both of you guys got it correct, but your neon must be wet. Think about it closely. Okay, if you look at the periodic table, this is period 3. Magnesium, aluminium, all that. But if you see, neon is all the way here on the periodic table. What does this imply? You are removing the first electron from each element, right? The first electron from neon is being removed from where? It's on the other period, right? If you must check yourself, you compare neon and sodium. Neon is 1s2, 2s2, 2p6. Sodium is 1s2, 2s2, 2p6, 3s1. Then magnesium is 3s2. Aluminium keeps going on and on. Where is the first electron removed from in neon? Period 3 is removed from at least the 3rd quantum shell. Period 2, like neon, is removed from an inner quantum shell. So where should your neon? higher, is it like here higher, where? Higher than everything else. Can see that? So you want to go to the highest, I'll be this phosphorus, I need to see your neon way up here. Okay, the reason why people lose marks in the graph is because, number one, they forget that neon is in and it's a different period. The electrons removed from the inner shell. Number two, some people get that already, right? But they lose marks because they draw higher but not highest. So good that you realize about the highest. Okay, good. You don't need to join them together, but if you want to, go ahead. Okay, so you can do something like that. So please understand that different periods mean different number of quantum shells. So let's explain this, guys. You have 2 marks. 2 marks. 1 mark is to the graph. You only have 1 mark for explaining 2 things. So you shouldn't be writing a lot. You must gauge for yourself. Okay, so let's keep it short and fast. Why? We talk about sodium first. For sodium, right, you can just say first ionization energy generally increases across a period. Right? Then you can just say, hence, first IE of sodium is less than the first IE of magnesium. Now, we don't have to tell me about what it increases across the period. What the effective nuclear charge, all that stuff, right? We do have time. If you write, you're not wrong, but you're going to waste a lot of time. It's only for 1 mark. You need to allocate the time yourself. We still don't have our 1 mark yet, by the way. We still need to explain neon. That's how strict, right? Some of the exam questions can be. Not strict, sorry, demanding. They are very, very demanding. So I need you all to take a look at neon now. How do we explain neon? Maybe we can explain a little bit more. As I've already mentioned, the first electron is removed, goes straight into it from the inner quantum shell of neon. That's what makes it special. So you tell me what makes it special. It's removed from an inner quantum shell, thus, okay, goes straight into energy already because again it's only 1 hour. Thus, large amounts of energy is required to remove the electron. Okay, I know we talk about how you talk about attractions and all that stuff. Again, it's 1 mark. Let's get to it. Okay, so large amounts of energy is needed to remove the electron, and you can basically end off the answer. Yeah, you've gotten the point across. Okay, so it's all about inner quantum shell, large amounts of energy. Hello? See, I like that for 1 mark is even a little bit demanding already. Okay, and it's already very short. Okay. Part 2, you guys can go and try yourself because it's all about explaining these tips, which we really explain, so no point for me to do it with you guys again. Now, what we're going to do now, we're going to stop looking at first IE. We're going to look at different IEs. So can you all turn all the way up to the last question? So question 5, the Dunman High 2018 question. Is it the last question? One of the last, sorry. It's question 5. Okay, I need you all to try part 1 and part 2. Okay, give it a try. It's 1 mark each, very short. Okay, but it's not as easy as it seems. So 5 each. Okay, try part B after this is a good question. Okay, I've converted it into a line graph like that. Okay, because the bar chart takes a while for me to draw. Okay, it's the same thing, right? Okay. Now, guys, let's answer the first question. I think first question is a free giveaway mark. What's the equation for the third IE? Okay, so you see how the question now changed already. Third IE of J. Right? Okay, J. Okay, how do you write this? What's the answer? You start off with where are you removing the third electron from? J2 plus. Good. Okay, so I mentioned whatever in class, do you guys remember? Good. And J2 plus becomes J3 plus electron. Remember the gaseous state symbol must be there, it's part of it. Easy question. Okay, now let's look at part 2. Now, part 2, I know they ask you to identify. Identify means you get it, don't need to explain, move on. But I want you guys to explain also because we need to know how to prepare for the situation which they ask us to explain. So guys, they want us to figure out where N is. Okay, they can ask you whatever, they can ask you K, they can ask you P, they can ask you R. It doesn't matter because why? You have to understand these questions. All these elements are consecutive. Consecutive means the moment you figure out one, you just trace the periodic table, you can find like R. Does that make sense? Okay, so over here they want to find N, it doesn't matter what they want you to find, but here they want you to find this guy over here. How do you figure this out? What's the answer? Anyone? Okay, what's the answer here? Have you tried? Any guesses? Maybe your guess could be correct, you never know. Okay, so why is this difficult? You have to understand why a question is hard. It's because now, instead of first IE, where we are all very comfortable, now we have third IE. This is a bit tiring, right? Okay, why do we have so many ionization energies? Again, guys, you see the graph here, what do you look at? What must you look at? You must look at the largest thing, right? The largest thing is this dip over here. So guys, focus on just N and O, the two people who are involved in this dip. What does this imply, guys? Once again, you must have this idea in your head that the third IE means the third electron is getting removed. So in all of these elements, the third electron is being removed from J, third electron is removed from K, third from L, third from N, so on and so forth. So guys, can you tell me the third electron from N, where is it being removed from? Yes, the outer shell. It's so much energy to remove the third electron. So I want you to annotate the third electron in N, not anywhere else, is removed from N inner quantum shell. That's why it requires so much energy. Because the very next guy is super low. What does this mean? Where is the third electron removed from? Outer shell. Can you see the idea here? Here, also third electron, but in O is removed from the valence shell. Outer shell, right? So just based on this alone, it's really up to you guys to see already. Guys, we are talking about N, right? If the third electron of N is from the inner shell, that means the outer shell got how many? 2. So is it group? 2. That's the answer. Okay, so third electron in N is removed from an inner quantum shell. That's why it has 2 valence electrons. Similarly, guys, you can also look at O's perspective. O, the third electron is removed from the valence shell. So how many valence electrons does it have? 3. Just nice. Okay, depending on which one you prefer. I prefer the inner one. Okay, but anyways, this guy has 2 valence, this guy has 3 valence, which makes sense. He's in group 13. And it's consecutive throughout. So guys, what's the element N? We can't just say group 2. That's not correct. Okay, how do we identify the element? Because group 2 got so many things, right? Group 2 starts off with like beryllium and magnesium and all that. Okay, but in this case, guys, you all take a look. It's 9 consecutive elements in periods 2 and 3. So that means these 9 elements, right, is period 2, then after that is period 3. So here what's the answer? You all don't have the periodic table, is it? Yeah, okay, next time try to have the periodic table beside you. If not, you can't figure this out also. Okay, but if you look at the periodic table, right? Between period 2 and 3, the overlap, right, will only be magnesium. Group 2 lah. Okay? You don't believe you can list down everything else. After magnesium, it's aluminium, silicon, phosphorus, sulfur. You go backwards, it's the sodium, neon, fluorine, oxygen. Can you all see it's period 2, then period 3? It's overlapping each other. If you were to choose something else, right, it'll be like period 3 and 4 already, something like that. Then you not working. Okay, can? So once you label out everything, right, you can pretty much do the rest of this question yourself, which is not what I'm concerned with. You all can go and explain everything yourself. Okay, but the idea is this, guys. Just now, remember the previous question that we did? Is sodium and neon that has the huge dip, right? But why here don't have? Why here is normal? Because it's the third electron, not the first electron. Just now the first electron, then you see the dip. But now it's not as straightforward. That's why you guys must always look at the large dip and contextualize it this way. Okay, and rotate the graph, and that's pretty much all we have. Okay. Now, we started a bit late just now, so I want you guys to try one last question, part B. Part B is good. Okay? Looks like a normal question. Okay, give it a try first. Okay, the first question is to ask you to explain, but try not to just copy from the notes. Okay, try to remember what I explained earlier on. Okay, then you write down the explanation yourself. Okay. It's part 2. It's a bit more interesting. Right? Part 1 can be found from the notes, so I don't really care. Right? Part 2 is an application. See whether you can deduce what they want. Okay? Okay, so part 1, I'll just write down the answer in a bit. Okay. Answer for part 1 is on the board. So this is successive, i.e., they're asking you why it keeps increasing, right? That's the general trend. So that's exactly what I explained just now. As you remove more and more electrons, the cation ion is just going to become more and more positively charged, which makes it even harder to remove the electrons as well. Make sense? Now again, the more you write, the more you will start to remember. So that's why we can start as early as now. Okay, but I'm interested in part 2. Draw the orbital. Okay, we learned about drawing of orbitals, but it's where the 5th electron is removed from. Okay, is it an s orbital, p orbital? You have only one choice here. But how do we do this? Guys, we have to slowly look at it from the start. What's the purpose of this graph? A successive ionization energy graph is to determine its identity. So guys, can you all tell me, right, what's some information you all have gathered from this graph? Okay, what group is it from or whatever? Okay, how many valence does it have? 5. Okay, from 5 to 6, the 6 is in the inner shell. That means there are 5 valence electrons. Meaning to say, it is in group 15. Okay, but this is where the issue comes in. Group 15 got so many elements, right? Got, what's this? Nitrogen, got phosphorus, got so many things. The 5th electron can be removed from different orbitals, depending on which element it is, right? So we have to first identify which element it is. Is it nitrogen or is it phosphorus? As I say, you won't really go anything beyond that. Can we tell? Is it nitrogen or phosphorus? Guys, how many electrons are removed in total here in the graph? 7, but does that mean necessarily that it's nitrogen? It could mean phosphorus, but you only remove 7, they never show the rest. But in this question, I know there's 100% nitrogen because there are only 7 electrons removed. Go and read the question carefully. I'll look at the top. Did they say something that tells you, right, that it is all 7 electrons removed? Yes. See, I wrote that up there. The graph here represents all the ionization energies of element S. And that stupid word all, right, that's hidden in plain sight has tricked you then. Right, okay, so it's very difficult sometimes, right? Okay, but when you see something as inconclusive as 7, you must check the question again. They confirm tell you one. Okay, so over here, we know it's nitrogen. So now we can come up with nitrogen's configuration, right? 1s2, 2s2, 2p3. So guys, can you all tell me where the 5th electron is removed from? 2s. Okay, you remove the 3 then you remove 2s, right? But they want the orbital. So guys, how does the s orbital look like? Okay, go and draw a sphere. Okay. Go and draw the s orbital for me. And that's basically your 2s orbital. Guys, you need to specify 2s. Because s, if you just write s orbital, it could mean 1s. Which is wrong. Right? Okay, not 1s, also must specify 2s. Let's just draw it there. So this damn 1 mark, right, is already so much work to do. Yeah, that's how it works. Okay. So 2s orbital, something like this. Okay, there's just one more thing that I think I never covered yesterday. Okay, a 2s orbital versus a 1s orbital. Can you tell me what's the difference here? Okay, just take note. Is that the test? What's the difference between a 1s orbital and a 2s orbital? Again, the quantum shell is different, yes. Okay, but we are looking at the exact orbital itself, right? Is there any difference in features? Want to make a guess? Okay, yes, the quantum shell, but it's difference in size. Okay, take note. Who do you think is bigger? Very obviously. 2s, right? Because the 2s is the second shell, right? So it's definitely bigger. Okay, so a 2s orbital is larger in size than the 1s orbital. There's like one question, I think it's question 4, that they test on the difference. You go and try that yourself also, question 4. Okay, so this one they like to test on. Even during my A-level paper, I remember fondly the first question they asked, what's the difference in properties? And legit, that's freaking easy, right? Nowadays, no more. Nowadays, the first question not that easy already. Okay, but yeah, that's the idea. Any questions? Okay, next time they can ask you to draw the difference, and then you just make sure the circle is bigger, can already. Okay, hello, and that's pretty much it for today. Please feel free to try the rest of these questions also. Whatever that I picked out today are some of the more challenging ones that are worth talking about. Reading the rest, I think you guys can manage yourself. Okay, and that concludes atomic structure. Okay, can.